listener. Myself Satish Kumar, and today I am going to discuss about the second chapter of vector analysis, which is differential and integral approach in electromagnetic theory. Before this, we have completed the large discussion about the vector analysis of vector algebra, uh, subtraction, addition. Now today we will discuss about the differential and integral approach in electromagnetic theory. For that, first we should know about the differential length, which is dl. We can represent this differential length in all three coordinate system, which we have learned in the last lecture: the Cartesian coordinate system, the cylindrical coordinate system, and the spherical coordinate system. So this dl, here you can see this dl. So in Cartesian coordinate system, this is the representation. In Cartesian coordinate system, this is the representation of dl in cylindrical coordinate system and in a spherical coordinate system. The differential surface, which is represented by ds, d of s, is a small surface. So we can represent in all three coordinates, and differential volume we can represent in all three coordinate system. Now what is dl? Suppose this is the length of L, the length of this wire is L. So the small length we can consider as a dl. Okay. And if I will consider a small cross section of any surface, then it is called ds. And if I will consider a cubic one, so in this cube, if I will consider any cross section, or so that is called dv. Okay. So likewise we can represent. In this chapter, we will discuss about the differentiation of a scalar, differentiation of vector, integration of a scalar and vector, Laplacian operation, and Helmholtz theorem. And finally, we will go for the assignment. Now, one by one, we will discuss about these chapters. Differentiation of a scalar first. So, the differentiation of a scalar. So, here I have taken this v as a scalar point, and which is an increase of function from one point v to a neighboring point v of x plus dx. So a small change in x coordinate, a small change in y coordinate, and a small change in z coordinate. Okay. So how we can differentiate this v? So dv is, this is dou v by dou x dx, dou v by dou y dy, and dou v by dou z dz. Okay. Where this term dou v by dou x, dou v by dou y, and dou v by dou z are known as the partial derivatives of v with respect to x, y, and z. Okay. Now, if I will go for the differentiation of a vector. Suppose I have considered here a vector, and how I can differentiate it. So the differentiation of any vector we can represent using this equation, where these are the partial derivative of vector a. Okay, with respect to x, y, z. Now, if I will go for the differentiation of a vector, uh, so we will discuss the gradient. What is the gradient? So gradient is an operation which performed on a scalar function that result a vector quantity or function. So if, since the gradient of any scalar will give the vector quantity, so and it has magnitude and direction. Okay. So the magnitude is the maximum. Magnitude is what? Magnitude of the gradient of any scalar will show the maximum rate of increase of a scalar function at a point. And the direction of the vector function at the point is the direction in which the maximum rate of increase occurs. Okay. So these are the things which we can identify after getting the gradient of any. Okay. So how we can get the gradient of any scalar, that you can see here in Cartesian coordinate system. Okay. So in Cartesian coordinate system, first how we can express this del. So in Cartesian coordinate system, del can be expressed like this. In cylindrical coordinate system, del can express like this. In a spherical coordinate system, del can express like this. Okay. So in Cartesian coordinate system, the gradient of a scalar. So, so I have taken here the v as a scalar function, and I am going to find out the gradient of this v. So the gradient of this v is nothing but the dou v by dou x. Since this is the function of xyz, v is a function of xyz. This is a scalar. Suppose x square plus 2xy plus uh, xyz. So suppose this is a scalar quantity which is given as a function of xyz. Now, if you want to find out the gradient of v, then this is the process to find out, where ax, a cap x, a cap y, and a cap z will show the direction. Okay, and the magnitude you can find. So combined combinedly, you can say this is a vector quantity, isn't it? This is a vector quantity. So here you can say the gradient of any scalar will give the vector. Now, what is the equipotential surface? So the equipotential surface will show the gradient of v will be g. When it will show? If gradient of v will be 0, suppose v is a function of xyz, and if and at the end of gradient of v, if the value will come as a 0, then we can say that the surface is equipotential. Okay. Why? Because such surface has the scalar function v doesn't change. Okay. So because there is no change, so the value will be 0. Okay. Now come to the other coordinate system. So gradient of v can be find out in other coordinate system like a cylindrical and a spherical as given here. There are some computational formula of gradient which you can see here. So if you will find out the del of v plus u is also an scalar, v is a scalar. So both are the scalar function. So if you want to find out the gradient of v plus u, then how you can write? You can write in this way. Separately you can find. So that will be equal. If you have a two different function, two xyz function is multiplied, and then you are going to find out this gradient, then you can find out v del u plus u del v. If these are in the division form, then you can write in this way. And if a v function, v scalar function is written like this, v to the power n, and then you have to find out the gradient, then you can write n v to the power n minus 1 del of v. Okay. So these are the computational formula which you can use to find out the gradient of any scalar. Okay. Now the divergence. The divergence of a vector field A at a given point is used for measuring how much field diverges from the point or converges at the point. So first we have to know about the divergence from the point and converges at the point. Since we are discussing about the electromagnetic, so in electrostatic, the electric field intensity diverges. Means It's a spread out. Okay. So divergence means it's a spread out from the point, and convergence means it's a come in, means as an input, like a, so from positive charge, the electric field intensity will spread out, isn't it? But at negative charge, electric field intensity will come in. So this is the example of divergence and this is the example of convergence. This is a simple way to understand this divergence and convergence. Okay. So in coordinate system, we can represent here, we can write the divergence of A, since this is a vector. So divergence of A will give an scalar quantity. So this is the whole one is a scalar function. Output is scalar. So divergence of A will give the scalar value. Okay. Divergence of a vector A, divergence is expressed as this one. Then A is called solenoidal field. And if I will find out the divergence of any vector, any A vector is the A vector. So if I will find out the divergence of any vector and get the result as a 0, then we can say that vector is a solenoidal field. Is it correct? In coordinate cylindrical coordinate system, we can represent the divergence of any vector by using this formula, and in a spherical by this formula. Okay. Now, some important point we have to note about the divergence of a vector field. So it produces a scalar field because a scalar product is involved. As we have seen that it will produce a scalar field. The divergence of a scalar is this one. So no make change. Okay, because it is giving by using the gradient only. Now here the divergence of A plus B. Here A and B are two vectors, two different vectors. So if I am going to find out the divergence of A plus B, then divergence of A plus divergence of B, in this form we can find out. If I will go find out the divergence of VA, where V is a scalar function and A is a vector function. So if any vector is multiplied with any scalar, and then after that we are going to find out the divergence, then in this way we can find out the divergence. Now curl is nothing but the rate of change of the vector field. So in coordinate system, Cartesian coordinate system, we can find out using this one. Since this is a vector and this is also a vector, so two vector cross multiplication we can perform by using the determinant method, as I have discussed in the previous lecture. If you will unable to find out the determinants of this or any problem regarding the cross product, then you can watch my previous lecture. Curl of a vector whose curl is expressed like this, where A is a vector, and if it will give the value as a 0, then it can be say irrotational field. Okay. In cylindrical form also we can represent this curl of A, and in a spherical coordinate system we can represent as this one, curl of A. Now integration of a scalar and vector. So first we will know about the divergence theorem. Okay. So in differential approach, what we have seen, the divergence of a vector can be represented like del dot O. Divergence theorem says that the volume integral of divergence of a vector field A taken over any volume V is equal to the surface integral of vector A taken over a closed surface enclosing the volume, which is total outward flux of the vector field A to the surface. Mathematically, we can represent, so this is the divergence of vector field A that is taken over volume V. So this divergence of any vector A taken over volume we can find out in a circular enclosed closed surface integral. Okay, like this. Some important point about the divergence theorem is divergence theorem applies to any volume V that is bounded by a surface S. The direction of this ds is always outward normal or normal to the plane that is the perpendicular to the surface ds. So suppose if I want to find out the surface, if I will consider this surface and this is the your ds here. So what is the direction? The direction will be outward normal. So which is normal to this one. Okay? Outward normal. This theorem is also known as the Gauss law. This theorem is useful in replacing a surface integral by a volume integral and vice versa. So we can replace it a surface integral by volume integral, or we can replace the volume integral by surface integral. Okay. And next one is a Stokes theorem. Stokes theorem. So a curl of vector we can represent in differential approach like this, as we have discussed earlier. Now the theorem says that the surface integral of curl vector A, which is taken over the open surface, this is the open surface, okay, is equal to the line integral of vector field A or the closed contour integral of vector A taken over a closed curve C bound the surface area S. So this theorem is useful in replacing a line integral by a surface integral. So we can replace the line integral by a surface integral or surface integral by line integral. Okay. Here one example is given. This is the example that is given. If vector is given here xy a cap plus x minus y ay cap, and another one vector m is given zx ax a cap x cap. We have to find out the curl of f first and after that divergence of m. So curl of f we can find out like this using determinant method. So we can find out like this, and divergence of a m we can find out like this. Okay. Now Laplacian operation. This operation can be performed both in a scalar and vector. Laplacian operation of a scalar is nothing but the 2 times divergence. You can see. Okay. So it is nothing but the defined as the divergence of gradient. It's not 2 times. It's a divergence of gradient. This is the gradient part, right? This is the gradient part, because this is v is the scalar one. Okay. So the this one is the gradient and this is the divergence, not 2 times the divergence. It's a divergence of gradient of a scalar. Okay. So this will give, so here divergence sorry, gradient of v will give the vector field, right? Vector field. So gradient of v is a vector and divergence of a vector, now this becomes a vector. So divergence of any vector will give the scalar. So the whole will give the scalar one. Okay. So del square v will give the scalar. Okay. This operation can be performed in all three coordinates. Laplacian operation of a vector A is defined as the gradient of divergence of v. So how I can represent if I will go for the Laplacian operation of a vector? Before this I have done here the Laplacian operation of a scalar. Now we will do the Laplacian operation of vector. So if I will go the Laplacian operation of any vector, then we can represent like this. Okay. So this will give the scalar one. Okay. Divergence of any vector. So divergence of any vector will give the scalar value. So this is the gradient, right? Now this becomes gradient. So gradient of divergence of A minus curl of A. Okay. This operation can be performed in all three coordinate system also. So this becomes vector, this becomes vector. Okay. There are two identities of vector analysis which is known as a null identity. This is the a special identity. So curl of gradient of A will give the 0 and divergence of curl of A vector will give the 0. These two identities you have to use in future. Now Helmholtz theorem. Helmholtz theorem says suppose this f is a vector quantity. So divergence of f is rho v and curl of f vector is rho s. So a vector f satisfying the above condition rho v and rho s, where rho v is volume charge density and rho s is surface charge density, which vanishing at infinity can be written as the sum of two vectors, one irrotational and other solenoidal. Okay, solenoidal divergence will be 0 and irrotational curl will be 0. Right, here you can see the divergence and irrotational. Curl will, if curl will be 0, then we can say the vector is irrotational, and if divergence will be 0, then we can say solenoidal. So here you can see the curl will be 0, so this is the irrotational, and this divergence will be 0 means the solenoidal. So by using this, the sum of these two, we can define it the F1. That this is the Helmholtz theorem. Later on, we will discuss briefly about the Helmholtz theorem. Okay. Some classification of vector. Suppose a divergence of any vector is 0. So divergence of any vector is 0 means solenoidal. Okay. And curl of A is also 0, irrotational. So if any vector A is solenoidal as well as irrotational, then we can say that a static electric field in a charge free region. Okay. Now, if divergence of A is 0 but not irrotational, then we can say a steady state magnetic field in a current carrying conductor. Okay. And if it is a irrotational only, not solenoidal, then we can say a static electric field in a charge region. And if both should not be equal to 0, then electric field in changed region with time varying magnetic field. Okay. So these are the conditions to significance this vector field. Now come to the another example. If gr is given, this g vector is given, determine the flux of this g out of the entire surface of cylinder where rho and z is defined. Z will vary from 0 to 1 and rho is given 1. Confirm the result using divergence theorem. So if psi is the flux of g, so how I can get it this flux? So it's a closed interval of g dot ds, isn't it? G dot ds of closed interval means what? P, B and S. So psi t, psi b, psi s are the flux through the top, bottom and sides, okay, of the curved surface of the cylinder. Like here you can see this is the B side, bottom side, this is the top side, and this is the side, surface side. Okay. So likewise, your outward flux will come out, isn't it? So it is the sum of all fluxes, psi t, psi b, and psi s. Okay. So for psi t, z is given 1, and what is the ds for this? Ds will be rho d rho d phi dz. So I will put it here for psi t, and I can get the final value psi t. Likewise, psi b you can find out that I have discussed the ds, no? So this ds will put here, okay, for different surface. Now the total flux we can find out the top flux, bottom flux, and surface side flux, and it will give the value 0. Since S is closed, the surface is closed surface. So we can apply the divergence theorem. This is the alternative. This is one method. But alternatively, we can do by using the divergence theorem. So since it is a closed surface, so we can replace it by using divergence. So divergence of G we can write and here dV over the volume. Okay. So directly we have to find out divergence of G only. So divergence of G once we will get, then we can write this one over 0. So the result is same here and here. Okay. So using two methods I have discussed, I have discussed to find out the this flux here, right? Using divergence theorem method and using cylindrical method, formula based method. Okay. Now here, suppose you have to find out the curl of a vector field, which is given in the previous example, PQR, PQT. Okay. So how we can find out this one? So P is given Px, Py, Qz. Q is given Qx, Qy, Qz. Sorry, Q rho, Q phi, Qz. And T is given Pr, T theta. T phi. Okay. So likewise in all three coordinate system, we have we have derived curl of a vector. Okay. Now these are the assignments which have total 10 question. You can try and you can ask anytime to my mail ID which I have mentioned here, which I have mentioned here. So you can ask if you have any doubt. Okay. Thank you.